Well, hello there, good people. Today we are talking about types of heat transfer. Now, you might be saying, Ms. Wilson, we already actually talked about heat transfer before. Well, yes, that's absolutely true. We did talk about heat transfer before. But before we talked about heat transfer mathematically, now we're going to talk about heat transfer conceptually. Before we learned that Q is equal to mc delta T and that Q equals ml, and that is most certainly a type of way of talking about heat transfer. But we can also talk about why that happens in the deep down, like what is going on back behind that makes the heat go from one place to another. What's the concept behind that? And we will see that there are three types of ways to transfer heat. We have heat transfer by conduction. By conduction, heat transfer by convection, and heat transfer by radiation. Those are our three types of heat transfer. We'll start by talking about heat transfer by conduction, then we'll talk heat transfer by convection, then we'll talk heat transfer by radiation. Heat transfer by conduction, I will give you a quick definition. Heat transfer by conduction is heat transmitted due to successive collisions with neighboring molecules and electrons. Heat transfer by conduction is heat transmitted due to successive collisions with neighboring molecules and electrons. That's it. If you do need to pause the video, get it written down, make sure that you do get that definition down, and let's talk a little bit about what happens. What happens with heat transfer by conduction is that you have some molecules that are moving very, very fast. Those are what we call high temperature molecules because they have a lot of kinetic energy. When those molecules are in contact with some other molecules that are at a lower kinetic energy or at a lower temperature, those fast-moving molecules will fly into the slow-moving ones, and the slow ones will go flying off. Now, what you get here is you get a little bit of collision where you get some conservation of momentum that happens. So the one that was moving fast is going to transfer some of that kinetic energy to the other one that was moving slow. Then the one that was moving fast to start with will now move slower, and the one that was moving slow to start with will now be moving faster. When this occurs, you get a back and forth transfer, back and forth, until everybody is kind of moving with the same amount of kinetic energy. That is a state at which everything will be at the same temperature, and we are in what we call thermal equilibrium. Heat transfer by conduction requires things to be in physical contact with each other. The molecules have to be able to run into each other. If things aren't in physical contact with each other, well then they can't have any heat transferred by conduction because their molecules can't run into each other. So heat transfer by conduction can only happen when things are in actual physical contact with each other. They have to be touching each other. Not all things transfer heat with the same level of goodness. Like, not all things are as good at transferring heat as all other things. We say that there are two types of materials in the world. We got conductors, which are very, very good at transferring heat both ways, and we have insulators, which are not very good at transferring heat. Conductors are very good at giving heat. They're also very good at receiving heat. Insulators are not good at giving or receiving heat. What determines whether something is a conductor or an insulator depends on the molecular structure of that substance. If molecules are all pretty stiff and don't really have very much mobility, if they're all kind of stuck where they are, and they're all kind of rooted and grounded, if you have one little molecule that comes in moving fast and it tries to hit the guy who's really kind of stiff here, then that guy will maybe move a little bit, but then he hits the other guy who's also very stiff, so who maybe moves just a tiny bit, and then the last guy here is kind of barely moving at all. And so you can see that things where the molecules are very stiff don't have very good heat transfer, whereas if these guys were really loosey-goosey and they had very good mobility and a little molecule came in moving very fast, well then this guy would go flying, run into this guy who would go flying, would run into this guy who would go flying, would run into this guy who would go flying, would run into this guy who would go flying. So you see much better heat transfer for things that are substances that have some molecules or some particles that have a little bit more mobility. If their molecules are too stiff, then they don't have good mobility. Then we also see that the other thing that's going to matter is going to be, how tightly packed the molecules are. If the molecules are really spread out, like this, and this little guy hits this little guy, well, this little guy might start moving. And if all of these are really spread out, I drew them in a nice line here, but they might not necessarily be in a nice line. Maybe this guy isn't down here, maybe he's up here, and maybe this guy is down here. And so if they're not very close together, then it's going to be a long time before this guy hits anybody, if he does hit anybody. He might not even run into everybody if everybody's out of the way. If you've got molecules that are really spread out, then that makes for a pretty poor conductor because the heat is very hard to transfer. But if you have molecules that are really tightly packed together, then molecules that are really, really tightly packed, well, one will run into the next, 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 because they're all right next to each other. So inevitably, they're probably going to run into each other. So we see that the things that really matter here for whether you're a good conductor or a good insulator, or in other words, a bad insulator or a good conductor, really, you could say it either way. If you're a good conductor, you're a bad insulator. If you're a good insulator, you're a bad conductor. But anyway, the main point is the main things that really matter here are the stiffness of the molecular structure. Do those little particles have room to move around? Do they have a little bit of freedom? Are they kind of loosey-goosey, or are they really tightly bound in their spots? And then also, are they tightly packed together, or are they more spread out? Things that are good conductors are things like metals. Metals are great thermal conductors because their molecules are, or I guess they're atoms in a metal. Their atoms are tightly packed together, but they also have these really nice mobile electrons that have a lot of freedom to move around and kind of like run into each other and move pretty fast. So because of that, metals become very, very good thermal conductors. Good examples of insulators are things like styrofoam. Whoa, foam. That's an O, by the way. Styrofoam, things like wood or like paper or air or rubber or like most liquids and gases. Those are all examples of good insulators. Some for different reasons than others. Styrofoam is a very good insulator because its molecules are all very rigid and kind of stuck where they are, so that makes it a very good insulator. Air is a very good insulator because its molecules are all very spread out. And so being so spread out, it's really, really hard for one to run into the next. You know all about conductors and insulators because you live in the real world, and so you just experience conductors and insulators all the time. In the morning, when you step out of the shower, you have some options on where you put your foot. You could take your foot and you could put it on that nice fuzzy bath mat, or you could take your foot and you could put it on the bathroom tile. Which one's a more comfortable experience? Well, the fuzzy bath mat, of course, not just because it's fuzzy, although that is an additional benefit. But one thing is you'll feel that the bath mat actually feels warmer than the bathroom tile. Is the bath mat warmer than the bathroom tile? No, they're in the same room at the same temperature in thermal equilibrium with each other. So the temperature of the bath mat is actually the same as the temperature of the bathroom tile. But the bathroom tile is most likely a much better conductor, whereas your bath mat is a much better insulator. Insulators like to keep their own heat, and they say, you keep yours and I'll keep mine. So the bath mat, when you step onto the bath mat says, excuse me, you please keep your heat and I'll keep mine, thank you very much. And you shake on it, and the bath mat keeps its heat, and your feet keep their heat. But conductors are very good at taking heat, and they're also very good at giving heat. You put your very warm foot onto the tile of your bathroom. And when you put your very warm foot on the tile, when your foot is a higher temperature than the tile, then the tile, which is a conductor, will suck the heat right out of your feet. And your feet says, oh, it's so cold. Not because the tile is actually cold, but because the tile is a very good conductor. So it takes heat away from your heat, heat away from your feet, leaving your foot feeling colder than before. You know this too because you made cookies before, and you know when you make cookies and you go to open up the oven to take that sheet of cookies out, you don't put your bare hands in there. No, that's crazy. You'll put on an oven mitt, or if you're kind of like me and you like to live on the edge, then you'll just take a little towel and you just kind of wad it up a little bit, and you're like, oh, this is fine. Hey, do you put that glove on your hand, or do you put that little wadded up towel on your hand? Is that to protect you from the air in the oven? The air in the oven is very, very hot, but you're not nervous about the air in the oven burning you. No, you're nervous about the baking sheet that the cookies are on burning you, or the sides of the oven, or the rack in the oven. You're scared about that. You're not scared about the air in the oven. Hey, which one's hotter? The air in the oven or the baking sheet in the oven? Same temperature. They're both in the oven. They're in a state of thermal equilibrium. The temperature of the baking sheet is the same as the temperature of the air in the oven. They're totally the same. But one burns you and the other doesn't. Why? Well, because air is a very good insulator. It's a very poor conductor. It doesn't transfer heat to your hand very well. But metal on that baking sheet, that's a very, very good conductor. You touch that baking sheet with your bare hands and you are feeling quite uncomfortable. because that metal is a very, very good conductor, and it'll say, oh yeah, you want a little bit of heat energy, and it'll just give it straight to you. Conductors, things like metals, are very, very good at giving away their energy or taking energy, and so in that case, the metal will give energy to your hand, and your hand will feel very energetic. Let's talk a little bit about convection. Oh, sorry, one other example about conduction. That's embarrassing. I can't believe I almost just skipped over it. This is why you'll see that most windows on houses are double paned, because that actually saves you money for your electricity bill. What happens is in the wintertime, you'll notice that your windows have a layer of glass, then a little gap, then another layer of glass over here so that you have a 2-pane window. It has 2 panes of glass. That's because inside your house during the wintertime, you turn on the heat, and the heat is really very nice and warm. That heat will run into the glass. Now, glass is kind of in between a conductor and an insulator. It's not a great conductor. It's not a perfect conductor like a metal is. It's also not a great insulator. It's kind of sort of in between. So that heat hits the glass, and it passes through pretty well. Gets to the other side, and then on the other side is a little pocket of air. Now, that pocket of air is a nice insulator, and so the heat doesn't make it very, very far through that pocket of air, and it hardly ever makes it to the second glass. This is great news for you in the wintertime, because that means that the heat mostly stays inside of your house. If you had a single pane window, then the heat from your house would hit that window and make it out into the outside world and be gone forever. And so we have double paned windows because it saves you on your electricity bill, because it keeps the heat inside the house. And those are a few examples of conduction. Next, we're going to talk a little bit about convection, and I'll start by giving you a definition. I would definitely most certainly write this down somewhere. Convection is heat transferred or heat transmission by means of currents in fluids. Convection is heat transmission by means of currents in fluids. Convection is heat transmission by means of currents in fluids. Oh, and bye, I guess. That's unfortunate. Oh, tough. Let me go find my camera. 1 second. Okay, that was very strange. Interesting times. Okay, here's my camera back. Okay, heat transfer by convection. When we talk about heat transfer by convection, the phrase that students always know is that hot air rises. Here's the idea of convection. Oh, there's a bell. Here's the idea of convection. Okay, the idea of convection is that the air heats up, and when the air heats up, it thermally expands. And when it thermally expands, well, now it's displacing a greater volume of air, which means the buoyant force, which is equal to the weight of the air that's displaced, that buoyant force just got bigger. And if the buoyant force just got bigger, then boom, it rises upwards. And so when things get warm, they expand, and then they take up more volume, so the buoyant force increases, so they go up. Then, if something gets cold, it thermally contracts, meaning it takes up less space, so the buoyant force is less, and those things sink down to the bottom. This is how a lava lamp works. On the bottom of a lava lamp, you got a little light bulb, and then on top of that, you got a little layer of some stuff, some gooey stuff. The light bulb heats up the gooey stuff. The gooey stuff, when it gets warm, it expands. When it expands, it experiences a buoyant force that's greater than the buoyant force that it was experiencing before. It rises up towards the top. When it gets to the top, it cools down. When it cools down, it contracts. When it contracts, it's less dense. It's taking up less volume. And so then the buoyant force on it is less. It sinks back down to the bottom. When it gets down to the bottom, there's a little light bulb to warm it up. It thermally expands, rises up towards the top, cools down, contracts, sinks back down towards the bottom, gets to the bottom, expands, rises up towards the top, cools down, contracts, sinks down to the bottom, and so on and so forth. And that is what we call a convection current. It's this movement of the up and the down and the up and the down and the up and the down as things heat up and then cool down and heat up and then cool down. That's the idea of convection. Now, in class, I do a little demonstration here that I'll draw for you. I talk to students about actually, I don't really like that color. I take everything back. Let's do yellow. Yeah, I'm going to do gray actually to start, and then I'll do yellow. Okay, what I do is I have 2 candles. Here's one candle. Here's another candle. And I teach students about how to roast a marshmallow. And we do this over the little candles like this. Boop. Boop. Now I take 2 marshmallows here. And I put one marshmallow next to the fire like this, a little tiny marshmallow next to the fire. And I put another little marshmallow above the fire like this. And I asked them, hey, which one do you think is going to cook faster? And by the time I asked them which one do you think is going to cook faster, this marshmallow is already on fire and this one is still looking white and squishy. Meanwhile, this one is burning up like crazy. What's the difference here? Well, this little marshmallow that's sitting right next to the flame here, it is experiencing a little bit of heat transfer by radiation. So it is experiencing some radiation. But this guy here is experiencing radiation from the fire, and he's also experiencing convection as really hot air that starts down near the flame rises upwards. That really hot air that's down near the flame rises upwards and hits this little guy, and he gets smacked with a whole bunch of very, very hot air, and so he cooks up really, really quick. Meanwhile, this guy's experiencing just a little bit of radiation, but the air that gets really hot goes upwards. It doesn't go sideways. And so this amount of air here is not the really hot air because the hot air is going up. So there's a little tiny bit of a little layer of air here, and that layer of air is acting way more like an insulator. It's keeping this little guy safe from the heat of the flame. Meanwhile, this air here is just getting so hot that it's just roasting that marshmallow, literally. And it's turning all like black and burnt. And if you like your marshmallows burnt, then that's a happy thing. And if you like them golden brown, then that's tough. So here's what we talk about. We talk about how this guy is getting blasted by convection and by radiation. This guy is just getting blasted by radiation, and this air actually provides a nice little cushion between the radiation from the flame and the little marshmallow. So that's a few tips for your next camping experience. The last type of radiation, or the last type of thermal, let me try again. The last type of heat transfer that we discuss in class is radiation. Radiation is the transmission of heat energy by electromagnetic waves. Radiation is the transmission of heat energy by electromagnetic waves. Hey, question for you. How does the heat from the sun get to us? Does it get by us? Does it get to us by conduction? Does the sun reach out and touch the earth and heat it that way? Is that what happens? No, because if the earth was touching the sun, then we would be dead. Does the sun heat the earth using convection? Does hot air near the sun expand thermally, and then as it expands, it rises up towards the earth, and the earth says, oh, look, a nice little gust of warm air coming from the sun. Is that what happens? No, that is not at all what happens. What happens is that the sun transmits energy to us through electromagnetic waves. Now, when we say electromagnetic waves, what we're really talking about is light waves. Electromagnetic waves is a fancy way of saying light waves. A very fancy way of saying light waves. And now there are lots of different types of light waves that come from the sun. Some light waves that come from the sun are visible light, which is what allows us to see. So that is spectacular. Other types of light that come from the sun we can't see. There's a type of light that comes from the sun that we can't see called infrared. Infrared radiation, or infrared waves, or infrared light. All saying the same thing. Infrared waves are what we feel as heat. What happens is straight infrared waves come down from the sun and they hit you. When they hit you, they are just carrying tons of energy. And that energy, when it hits your little molecules, it makes your little molecules go brrr, and then all of a sudden your molecules start to move. And if they're moving, bam, we got kinetic energy. And that increases the temperature of stuff. That was the whole idea of infrared waves, or of radiation. Something that you should know is that radiation does not need a medium to travel through. Unlike conduction, which needs, like, you need molecules that can run into each other in order to get heat transfer by conduction, or something like convection, where we say, hey, you got to have a fluid that then expands and then rises up. You need to have those fluids in order to transfer that heat. In radiation, it's not true. Radiation can come, oh, actually, this is true of all electromagnetic waves, but electromagnetic waves can come straight from the sun to us, even though there is nothing but space in between. They can travel through, they don't need a medium to travel through. They don't need something like some sort of solid or some sort of liquid or some sort of gas. They can travel through space. Now, the truth is that all bodies, meaning everything, absorbs and emits radiation. Let me try again. And emits radiation. All bodies absorb and emit radiation. So, for example, you right now are absorbing some radiation from the sun and also from like the environment around you, and you're also emitting some back out. The desk in front of you is emitting some radiation, and it's also absorbing some of your radiation. All bodies, anything that has matter, really, anything that's made of mass anything that has mass is made of matter, is going to absorb radiation and also be able to emit radiation. But the same way that we have with conduction, the same way that we have a way to talk about things that are good at this and things that are bad at this, we have something similar with radiation. Sorry, I gotta move that guy out of the way. With radiation, we talk about absorbers or emitters. You'll see in a second we use both interchangeably. And then we also talk about reflectors. An object that is a good absorber of radiation is also a good emitter of radiation, and an object that's a good reflector of radiation is bad at absorbing and emitting radiation. You know about this because you know that there are certain colors that are good to wear on a hot day and other colors that are bad to wear on a hot day if you want to keep cool. You know that in the summertime, if you're wearing a black t-shirt, you're going to feel way warmer than if you're wearing a very light colored t-shirt. Why does that make a difference? Well, because black as a color is a better absorber and a better emitter of radiation. What that means is if radiation, infrared waves, are coming down from the sun, the way that the black interacts with those infrared waves is going to be different than the way that a light colored t-shirt like a white or a light pale pink, those are going to interact with those light waves very differently than the way that black is going to interact with those light waves. What's going to happen is the light waves as they come in, the black t-shirt is going to absorb that radiation and then spit it straight back out again at you. The same way that we say that conductors are very good at both taking in heat but also giving it away, like a piece of metal, if it's colder than you, then when you touch that piece of metal, it's going to steal the heat right out of your hand. And if that piece of metal is hotter than you, it's going to put that heat straight back into your hand. It's the same thing with absorbers and emitters of radiation. Absorbers and emitters of radiation, if it's a good absorber, if it's good at taking in that heat, it's also very good at sending it back out again. So if you get heat coming in from the sun, if you got infrared waves coming in from the sun, they hit your t-shirt, your black t-shirt, boom, absorbs them and then spits it back out again, and it spits it back out at you. And so you feel way toastier when you're wearing a black t-shirt. But if you're wearing a white t-shirt or a light colored t-shirt, then the light from the sun comes in, it hits your t-shirt, and that is a good reflector of radiation, a much worse absorber or emitter of that radiation. So it hits that white t-shirt and bounces back off again, and you don't feel that heat the same way that you do if you're wearing a black t-shirt. Generally speaking, things that are darker colored are better absorbers of radiation, and things that are lighter colored are better reflectors of radiation, the same way that they're good reflectors of light. Things that are good at absorbing light generally tend to be good at absorbing electromagnetic radiation, and things, infrared radiation. And things that are good at reflecting light generally tend to be good at reflecting back that infrared radiation. So, things like white, which is very, very bright because it's so good at reflecting light, or things like metallic-y kind of things like mirrors are very good at reflecting light. They're also very good at reflecting infrared radiation. Now, here's a question for you. On a night, at nighttime, if you go on a run, if you want to stay cool at nighttime, would you rather be wearing a black shirt or a white shirt to stay cool at nighttime on a run? Do seriously pause the video and think about it here, because this is a tricky one. If you want to stay cool at night, think about it. Where is that radiation coming from? What is making you so hot? Is it coming from the sun? No, because it's nighttime. The heat is coming from you. So you want to get that heat away from you as much as possible. I would rather be wearing a black t-shirt. If I'm wearing a black t-shirt, that black t-shirt will absorb the heat from me, because it's a good absorber, and spit it back out again into the world. And so the black t-shirt will keep me cooler because it's going to keep taking my heat out away from me. Take it in, spit it out. Take it in, spit it out. Take it in, spit it out. If heat was like an arrow, it would pierce straight through the black t-shirt and out into the environment. But if I were going on a run at night and I wanted to stay warm, I would want to wear a white colored t-shirt because the heat is coming from me. And when I wear that white colored t-shirt, well, the heat comes from me, it hits the white and bloop, reflects back and goes straight back to me. So then I still feel warm. I'm not losing as much as my heat to the environment. I don't know if you've seen before, but have you seen those ski coats that have like the little like dots on the inside? Like it's all like little it's like little tiny shiny dots all over the inside. These used to be a really big thing. They were like a really like cool thing. Like when I was in high school, if you had one of those ski coats that had the little dots in it, you were cool. You were and by cool, I mean warm. Because what happens is they would have like these little ski coats that have these little like shiny dots all lining the inside, and they would literally just line the inside of the coat with the shiny dots because the shiny dots are good reflectors. And so what would happen is you get on the ski slopes, you put that jacket around you, and as you try to emit heat out, it's a good reflector. So bloop, it just sends it right back to you and it keeps you way warmer. The little dots themselves aren't warm, but they're very good at keeping your heat in towards you. Question for you. If you poured coffee, and you poured a cup of coffee into a black mug, and then you poured the same amount of coffee, let's color it in here so that you know, and then you poured the same amount of coffee into a white mug, which coffee would cool down first? Take a quick guess. Oh my gosh, did you see that? It's Sammy Davis Jr.'s 100th birthday. Congratulations, Sammy. I don't know who Sammy is, so I don't really know what I just promoted, but I will find out afterwards. Okay, so if you have a black mug, then the black mug will emit radiation way better. If you have coffee inside of your black mug, then the black mug will absorb the heat from the coffee and spit it back out into the environment. And so coffee will cool down in a black mug very quickly. But if you have a light colored mug, then your light colored mug is a good reflector of radiation. That coffee has a lot of heat. That coffee will try to send that heat outwards, but then the light colored mug will reflect that heat straight back, and the coffee will stay warmer for longer. So if you like your coffee cool, go with a black mug. If you want your coffee to stay warm for longer, go with a white one. And that is all for today, folks. Today we talked about the 3 types of heat transfer. We talked about conduction, convection, and radiation. We talked about with conduction how they're conductors and insulators. We talked about convection is really just the idea of hot air rising. It's just the movement of the warm stuff goes up and the cold stuff goes down. Then we talked about radiation, how radiation is really just electromagnetic waves, and we have some things that are good absorbers and emitters of electromagnetic radiation, and other things are better reflectors. And that's all for today, folks. I do hope that you have a wonderful, wonderful rest of your day, and I'll see you all next time. Bye, good people.